While there is plenty of use in single sample hypothesis testing, once you start thinking about scientific questions of interest, you quickly realize that oftentimes when we're trying to ask a question in science, we're really thinking about comparing multiple different populations. And if we want to be comparing multiple different populations, we need to expand our understanding of the hypothesis testing framework to allow for there to be multiple different populations. And probably the most common way that this is going to be done is by thinking about two independent populations. So if we have population 1, we have population 2, we assume that they're independent of one another, then are we able to compare the parameters that characterize the distributions of the first population with the distribution of the second population? And that's the goal with comparisons between multiple independent populations. Often we'll be thinking about, say, comparing their means or comparing their variances. Right, so often we'll have these two populations of interest, and we want to compare them. In order to do so, we require multi-sample statistical inference. Okay, so introducing some of the notation that we'll require in order to do this, if we have two different populations that we wish to compare, then what we will assume typically is that we draw a sample of size n from the first population, and we'll label this sample x1, x2, up to xn. We'll also assume that there is some population mean, we'll call that mu x, and some population variance, so we'll call that sigma x squared. And this notation of using the subscript x here is just to highlight that this is going to be corresponding to the random variables denoted by x. Right? So we have x here. If we wanted to estimate this population mean, we could take the sample mean of x, right? So everything from the first population can be viewed as the same as if you're doing a one sample inferential problem. If you wanted to know, well, how does the sample mean perform, you can take the expected value of that. That will give you the population mean of x, and the variance is going to give you the population variance of x divided by the sample size, which is n in this case. Now, if we take a sample of size m from our second population, then we can denote this with y1 up to ym. So instead of using x, we're using y, and instead of there being a size n, there's a size m. Now, maybe they're the same sample size, maybe they're different, but we'll try to keep this as general as possible. We have our population mean is mu y, we have our population variance is sigma y squared. So we have the mean and the variance of this population. Once again, we can use y bar to estimate the mean of this population, right? And so this would be similar to doing one sample inference. We also can say, well, the expected value of y bar is going to be the population mean of y, so that's mu y, and the variance of y bar is sigma y squared, so the population variance divided by the sample size, which is m, right? So all of this is the standard result from one sample inference. Now, if we're interested in comparing the two population means, so we want to compare mu x to mu y, the question that we have to ask ourselves is, well, how can we do that given these two different samples that we have here? And one thing that I'll point out is that if you want to compare mu x to mu y, then what you can really do is think about the difference between mu x and mu y, right? Because if you want to know, are they equal? Well, that's the same thing as saying, is their difference equal to 0, right? And so often we can think about this as a difference in means. It's going to be a mathematically equivalent statement, regardless of whether you're doing differencing or if you're thinking about the means directly being compared. Now, if we want to estimate this difference, probably the most intuitive way that we could go about doing this is by taking our sample mean of x, our sample mean of y, and taking the difference between the sample mean of x and the sample mean of y. This is a fairly intuitively compelling estimator, right? Because we know that mu x is estimated well by its sample mean. We know that mu y is estimated well by its sample mean. And so if we want to estimate the difference, then we can consider the differences in sample means. And so if we're taking that as the estimator, and then we want to do statistical inference using that estimator, what we need to understand is the sampling distribution of that estimator. Okay, and so if we think about this estimator in a little bit more depth here, right? So we want to know, well, what is the distribution of x bar minus y bar? And what we will do to arrive at this is to assume that x and y are independent. So if x and y are independent, then knowledge about x doesn't inform anything about y, and vice versa. We write this notationally as x and then this perpendicular sign y, right? So this says x and y are independent of one another, okay? Now, if we know that they are independent, then information is not sort of traveling between them. This is oftentimes going to be a reasonable assumption, but perhaps not always, okay? And so we can use this result to determine the sampling distribution. So if we have our independence, then we can write out the expected value of x bar minus y bar is the expected value of x bar minus the expected value of y bar, which is the difference in means, right? So in expectation, they are actually going to equal the difference in population means, which is what we want. I will note that formally, this first point does not require independence, right? So right here, we get this regardless of whether they're independent or not. However, the second point that we want to make, which is about their variances, does require independence. And so that's why we make this assumption here. So if we take the variance of x bar minus y bar, and we know that they're independent, this is going to give us the variance of x bar plus the variance of y bar, which results in the variance being added together of these two terms, okay? And so because we know that the variances add together here, right, then we know the population mean is the expected value, right? Then we can sort of work out the parameters of the sampling distribution in this way. Now, if either x and y are both normal, or if both of their sample sizes are large so that we can apply the central limit theorem to the sampling distribution, then what we're going to be able to say is that actually the differences in them are also going to be normal, right? So x bar and y bar are both approximately normally distributed, either because the populations are normal or because there's a large enough sample size that we can use the central limit theorem. And as a result, the mean difference is also going to be approximately normally distributed, right? So we take x bar minus y bar, that's going to have a normal distribution. The mean is going to be mu x minus mu y, and the variance is going to be sigma x squared over n plus sigma y squared over m, right? And so we have this result here is going to hold either approximately or exactly for the differences in means whenever we have large enough values for both n and m, right? So if our sample sizes are large, then this is going to hold. And because of this, once we know the sampling distribution is normal, we can then start to make use of any of the normal results in order for us to derive sort of inferential procedures here. And so if we know the population variances, then the normal sampling distribution is going to apply. If we take this through standardization, right, we take our differences in mean, x bar minus y bar, we subtract off the actual mean, which is mu x minus mu y, right? Divide that by the standard deviation, so the square root of sigma x squared over n plus sigma y squared over m, right? And then this is going to give us our standard normal here. This is the standardization procedure. Anytime we want to calculate probabilities from the normal, then that's going to work out. Now, if the population variances are unknown, so if we didn't know, well, what is the value of sigma x squared or what is the value of sigma y squared, right? If that's the case, then we can't use this directly, but instead we could estimate the population variances and then plug those in, right? So then we're going to get x bar minus y bar minus mu x minus mu y, right? So that's same numerator, but then we divide by the estimated standard error here, right? So sigma x squared over n, or sx squared over n, sy squared over m to replace sigma x squared over n and sigma y squared over m, right? So we replace this with the sample. As expected, this is going to end up causing a t-distribution to emerge as our sampling distribution. And the weird part that we're going to be running into here is how many degrees of freedom do we have? Okay. And in this case, the degrees of freedom is given by this somewhat ugly-looking formula over here. Okay, so to get this formula, we take our sample our sample variance divided by n, our sample variance divided by m. We square the sum of those two things, and then we divide by the sample variance over n squared divided by n minus 1, the sample variance over m squared divided by m minus 1. Okay, and so if you plug in this whole formula, that's going to give you your sampling distribution's degrees of freedom. Now, in practice, if you're doing this by hand, right, if you're using a computer, the computer will calculate this for you very quickly. If you're doing this by hand or you want to sort of have an approximation, some people will also take this to just be the minimum of n minus 1 and m minus 1. And this is always going to end up being a conservative estimate here, right? So you're going to end up with fewer degrees of freedom if you use this minimum, but obviously taking the minimum is a lot more straightforward than using this sort of more complex procedure here. So let's take a look at an example for this. Here, what we're dealing with is a psychologist who is trying to determine whether there's a significant difference in the mean levels of depression between two groups of patients, those who have received cognitive behavioral therapy, so the CBT group, and those who have received medication. The CBT group consists of 36 individuals. They have a mean depressive score of 12 and a standard deviation of 5. The medication group consists of 49 individuals with a mean depressive score of 15 and a standard deviation of 6. Now, what we want to write down is here the estimator, sampling distribution, and estimate used to compare the population means. If the standard deviations are population values, right? So if we have standard deviation of 6 being sigma, and same thing with the standard deviation of 5 here being a sigma. And what we are expecting is that mu x is equal to mu y. Okay, and so let's write down sort of all of the information that we've actually been given here. So if we call the CBT group population 1, right? So we have population 1. And we know that their sample size is 36, right? We have that the mean depressive score, so x bar, is going to be 12, and sigma x, sample stand or the population standard deviation, is 5. Okay. In our second population, then what we are told is that m is going to be 49. The mean score, which is y bar in this case, is going to be 15, and sigma y is going to be 6. Okay, so we're given all of this information. Now, what we want to know is, well, what should we actually use as our estimator? And remember that the estimator is going to, broadly speaking, be the standardized procedure. Right? And so what we'll do is we'll take x bar minus y bar, we subtract off the population mean, mu x minus mu y, right? And then we divide by the standard deviation, or the standard error if you'd prefer. Okay, and in this case, because we have the population values, we can use sigma x squared over n plus sigma y squared over m, right? And under the case of having the population values, we know that this estimator is going to be approximately a normal 0, 1. Okay. And so then by plugging in our actual values here, we can work out what is the estimate, but this is the general thought process that we have in this setting. One important piece to note is that if we think about this difference here, right, if we know that mu x is equal to mu y, right, then this difference here is equal to 0. Because if mu x is mu y, then mu x minus mu y is equal to 0. Okay. So we can start filling in sort of all of this information. Okay. To do so, we take that estimator. We know it's going to be a normal 0, 1. If we plug in our values, right, so we plug in our 13 minus 15 divided by our standard deviations over the population values, notice that the difference here that we're plugging in is exactly equal to 0 because mu x and mu y are equal to one another. Then we find that the estimate is negative 1.673. Right, so that we have our estimator, our sampling distribution, and the estimate. Okay. Now, what if we run the exact same procedure, right? So we have exactly the same information being provided here, right? So all of these values are the same. We still want to know mu x equal to mu y. However, we're not assuming that those are the population values, right? So instead, when we say standard deviation of 5, then we're actually assuming that that is the sample standard deviation. Okay, so what are we going to do in this case? Well, it's going to look basically the same, right? Except instead of us having a normal 0, 1 here, right, we're going to have a t-distribution with new degrees of freedom. And so how are we going to calculate this? Well, remember that the t-distribution, or the number of degrees of freedom, is going to follow that sort of very ugly looking formula, right, where we have something like sx squared over n plus sy squared over m squared, divide that by sx squared over n squared n minus 1 plus sy squared over m squared over m minus 1. right? So we have this formula. Again, there's a lot of terms in it, but really what we just need to do is we just need to plug in our values for s of x, our n, s of y, and our m, and then work through what that actually happens to be. Okay. And so then if we sort of plug in our values here, right, then we get our 5 and our 36, our 6 and our 49 all plugged in, and we find that the number of degrees of freedom is going to be 81.619, right? And so we can use that. The other option is that we could have considered, well, what is the minimum between n minus 1 and m minus 1, right? We have n is 36, m is 49, and so n minus 1 is 35, m minus 1 is 48, and so we could also have taken this to be approximately 35, right? Of course, this 81 is a lot larger than the 35, and so in this case, it's going to perform a lot better if we actually use this value here. But if you were doing this by hand or you forgot this formula, then that's going to work out well enough here, right? So we could take the degrees of freedom to be 35. If we want the estimate, notice that we're going to be plugging into the exact same formula as what we had before, right? And so the estimate is going to be the exact same value as well. So if we plug in all of our values into this formula here, right, then we end up with negative 1.673, just like we had in the previous example. Now, in this case, we've been working sort of through the most general of the assumptions, which is just that we have these two populations. They're not related to one another. They remain independent. Sometimes we're going to be willing to make a further assumption, and specifically, we're going to be thinking about making the assumption that we have equal variances between the two populations. Right, so the previous results are going to hold for any two independent populations, but if we have additional information, it might be useful to take that into account. So if we were to know, for instance, that the variances were equal, so we have sigma x squared equals sigma y squared, and we'll just say that that's equal to some common variance that I'll just call sigma squared here, okay? Then if we're going to be simplifying down this variance expression, notice that we have the same variance here, right? So it's still sigma x squared plus sigma y squared, but both sigma x and sigma y are just equal to sigma squared. And so we can sort of write it in this somewhat simplified manner here. Right? And so in this case, we don't actually have two variances, we just have one variance. So if the variances are equal, but they're unknown, then what we can do is estimate a common variance. Instead of us estimating individual variances, we could just estimate one variance overall. And in order to do this, what we're going to think about doing is sort of taking a weighted average between the variance of x and the variance of y. If we know that they're supposed to be the same, then it turns out if you take n minus 1 times the variance of x, m minus 1 times the variance of y, and divide that by n plus m minus 2, then that's going to give us what we call the pooled variance estimator, right? So we write this as SP squared, where the P is standing for the pooled variance estimator. We're pooling the information from x and from y together. And so if we take this pooled variance estimator, then we can end up using this if we're willing to assume that the variances are equal. If we end up doing this, right, we plug in our t statistic here. We have x bar minus y bar minus mu x minus mu y, right? And then if we're dividing by the variance here, well, the variance estimator is going to be this equation here, except with SP squared plugged in for sigma squared. And so then if we end up writing this out, we get SP times the square root of 1 over n plus 1 over m, right? And that's just the square root of this term right here, right? So if we take the square root of this term, if we've replaced SP squared with sigma squared. Okay, and so then we end up with this sort of modified version of the test statistic. Now, the main thing that's actually changing here is if we look at, well, what is the sampling distribution? In this case, our sampling distribution is going to become n plus m minus 2, right? And so if we take n plus m minus 2, well, then that's going to end up being sort of a simplified number of degrees of freedom, but it's also going to end up being a larger number of degrees of freedom, okay? And so in the case that we can have equal variances, then we can work out that this is our sampling distribution here. Okay. And so how does this apply in practice? Well, if we're going to work through the same example, right, so we still have our 36 individuals, mean depressive score of 12, standard deviation of 5, 49, mean depressive score of 15, 6, right, from our two populations. What is the pooled variance estimate and the corresponding sampling distribution and point estimate if mu x is equal to mu y, right? So we want to run this exact same procedure here, except let's assume that we're making the assumption that sigma x is equal to sigma y, right? And so then in this case, what we're going to do is, because we are assuming that sigma x squared equals sigma y squared equals sigma squared. Then we want to estimate this through the pooled variance. And so we have SP squared. And what we're going to do is we're going to take n minus 1, sx squared, plus m minus 1, sy squared, divide that by n plus m minus 2. And so once we've done sort of this procedure, right, we get our value here. And then our test statistic is going to be much the same, right? So we take x bar minus y bar minus mu minus x, or mu y minus mu x minus mu y, right? And then we divide that by our standard deviation, which is going to be our SP squared times 1 over n plus 1 over m, okay? And so if we plug everything into that, then we can work out what we'll be doing. This t is going to end up following a t distribution where we have n plus m minus 2 degrees of freedom. Okay? So those are the thought process. Now we can plug in to get sort of our results here. Okay? So for the pooled variance estimate, we take our formula here, we plug in our 36, our 5, our 49, and our 6, and we work out that that's going to be about 31.361. Okay, so we have that as our pooled variance estimate. Note that this is the pooled variance estimate, not the pooled standard deviation, right? So there should be a squared there. That's going to give us our 31. And so then our standard deviation is going to be the square root of that, okay? And what we'll be sort of working through is the formula that we have here, right? And remember, that's going to follow a Tn plus m minus 2. So in this case, if you add up 36 plus 49 minus 2, you get your 83 degrees of freedom here. And then plugging into our formula, we get our 13 minus 15, right? Mu x minus mu y is still 0. SP is going to be the square root of 31.361, okay? And then 1 over 36 plus 1 over 49, we plug all of that in and we get negative 1.627. So that's going to be the estimated value here. Okay. So when are we going to use this pooled variance? Well, the pooled variance should only be used when it is known that the populations share a variance, okay? So if you know based on context, based on subject matter, based on your actual knowledge of the situation, that the two populations have the exact same variance, then you should use the pooled variance. In every other situation, you should not use the pooled variance. Okay, so it's not advisable for us to test based on the data that we're looking at, or to use the data itself to inform whether or not we should use the pooled variance. We really need to be thinking about this as being driven from the subject matter. Okay, so if we have subject matter expertise and that tells us, well, these variances are going to be the same for whatever underlying reason, then we can use the pooled variance. If we don't have that subject matter expertise, then this is not something we should be doing. Right? So we need this reason to justify the equality of variances. If not, we really shouldn't be making this assumption. Okay? The thing that I'll point out is that very little is going to be lost if you assume that the variances are unequal, but it turns out that they actually are, right? So if you just run the test and you're assuming there are two separate variances here, that's going to be mostly fine, even if it turns out that those two variances should have been equal to one another. However, if you falsely assume that the variances are equal, you're going to lose a lot more performance. And moreover, if you test whether the variances are equal, and then you run your hypothesis test on the basis of this, then you're actually going to end up with a test that's not correctly calibrated to the levels that you need, right? So we can't use the data. We can't sort of falsely assume this. It should be a really conservative assumption. If you actually know for sure that the variances are going to be equal, then that's a reasonable assumption to make. If you have any doubts about this, or if you would need to look at the data to determine it, then just run it under the assumption that they're not equal and everything will sort of work out for you there. Okay. So in order to compare population means from two independent samples, the differences of the sample means can be used. This has an approximately known sampling distribution. Specifically, it's going to be normal using either the central limit theorem or the population distributions directly. And through this, we're going to be able to end up conducting inferential procedures because we know what our test statistic is, or we know what our estimator is, and then we know the sampling distribution, or we would know the null distribution. And so from here, we're going to be able to derive inferential procedures and actually test or estimate differences between independent population means.